Okay, so today we'll be talking about the simulation of the attitude determination system that we're flying on ECO this year, as well as some proposed filters that we're basing on Sanat's work that he's done throughout his PhD thesis. The reason why we're doing this is that the attitude determination system is mission critical. It's critical to the scientific payloads that we're sending up there, and it's critical to the satellite health itself. So if we can't control the attitude, we can't guarantee that we can charge, we can't guarantee that we can point our instruments where we want to point. The attitude determination system, so we're only actually talking about the determination part of the system today, that we'll be looking at is comprised of two cameras, so a flying sun and a Earth or an India camera to be specific, a gyroscope and a magnetometer, so a pretty bog stock standard CUBESAT attitude determination system. And in addition to that, like I mentioned beforehand, the base model is revolving around an EKF, and we also need to use a sun model and a world magnetic model, which I'll talk about a little bit later. To put a little bit of that requirement into perspective, in CUBE50, the requirement that I want to talk about today is that we were required to have a pointing knowledge of plus or minus 2 degrees. So while it is quite, it's not too restrictive, so it can be done on a CubeSat relatively easily. But the motivation is, the reason why we chose the EKF is that it's robust, mainly because it's robust, it's computationally cheap, and it's fast. It does fail a little bit when there are highly nonlinear dynamics or movement models involved. So this is why we want to have a look at using the unscented kalman filter. Traditionally, the UKF has been the answer to the highly nonlinear situations, but it's computationally expensive. So when we send up our CubeSat that has very limited resources, we want to make sure that we're using all of those to the best that we can. And we'll be looking at some new variants which Sanat has worked on, which drastically reduce that computational cost. The basics of the attitude determination system, I won't ski too much with this maths, is that we have two state vectors that we'll talk about. One is basically representing the attitude in terms of your Euler angles, and the other in terms of quaternions. I only mention the quaternion version of the state vector in the dynamic model is because that's what we're actually flying on ECO, because quaternions aren't susceptible to things like singularities when you're inverting the kinematics in your controller. All of the simulations we've done today based on these Euler models, and future work will be looking at implementing some quaternion-based unscented kalman filters. So essentially, your state is made up of your actual attitude, and when you're using a gyroscope, you also want to estimate the bias of those gyroscopes, because the bias itself exhibits a random walk process, so you need to track that over time. In your dynamic model, so this is the prediction part of the filter. Essentially, all you're saying is a high rate. What's my gyro measurement? Okay, I'll integrate the attitude according to that. And that's why we need to trace that bias so that we can properly integrate our state. The measurement model is relatively simple. We have some vectors, our Earth, our Sun, and our magnetic sensors that I was talking about, in an inertial frame, and we simply rotate that into the body frame, and that gives us an error, and that's used at the correction stage. And these inertial vectors are calculated based on that world magnetic model in ECO, or you can use any type of magnetic model that you like, which then results in the requirement that the attitude determination system needs a position fix. So then you've got all of these other things that Matt was talking about yesterday, where they use their GPS and they actually have an inbuilt, they have an orbit determination algorithm while we use an orbit propagator. And that is now time to hand over to Sanat, who's going to introduce the unscented kalman filter and how this will apply to the current attitude determination filters.
Thanks, man. So we'll not go over the extended Kalman filter. It's a pretty standard and it's a 60 years old algorithm. And unscented Kalman filter is relatively new. It's 17 years old. So in all the type of Kalman filters, there is two-step prediction and correction. So how EKF and UKF are different is mostly in the prediction stage. So let us introduce a very generic mathematical models that Ben was telling about. So it's we always express a system, how it evaluates over time using a stochastic dynamic model. So it's a differential equation and non-linear. So that is our model, and this is our this is the measurement. So measurement and system both are non-linear, and what UKF does is that based on the initial statistics, which is mean and covariance, it deterministically creates some grid points or sigma points, and then propagate each of them using numerical integration. So this differential equation is being propagated using numerical integration to next step multiple times. So that is why UKF is computationally expensive. In EKF, it's only one time we do this propagation, and UKF we do it multiple times for different sigma points. So suppose for this attitude determination problem, we are interested in 6 state elements. So 3 angular elements and 3 gyro rate elements. So in that case, we have to propagate 24 sigma points. I mean 24 times we have to do the numerical integration. So how we choose the number is 2n plus 1. If we have 6 state elements, then 2n plus 1, and that n has to is the double of the number of states. So due to this numerical integration, computation time is very higher, and for CubeSats, it's really hard to implement UKF because of the power constraints. And then there are several algorithms that there, like spherically simplex unscented transform and another MUT methods, but these doesn't reduce the processing time much. So what we are proposing to reduce the processing time is single propagation unscented Kalman filter. So here, similar to the EKF, we propagate only once, but still we use these sigma points or grid points, and so we know the difference. What is the difference at time at t between the mean and the other sigma points, and we use this difference here to recreate the points at the t plus delta t time. So we use only one propagation, and then we recreate the sigma points at this time without doing any other propagation. So that's how our this new algorithm reduces the processing time. But the problem is that in SPUKF, this recreation is done using a first order approximation. So to reduce that, to much more improve that, there is another method we have developed called extrapolated single propagation unscented Kalman filter. There we recreate these elements using second order Taylor-Series approximations. So we call this method as extrapolated single propagation technique, ESPT. So this ESPT is not only applicable for Kalman filter, that could be applied in other optimization method too. So this is the preliminary result for when we implement Kalman filters, extended Kalman filters, and UKF, SPUKF, ESPUKF in attitude determination. So you can see that this is the filter convergence time. These black lines are the EKF, and you can see that it takes almost 500 seconds to converge to nearly zero error. But the unscented type filters rapidly converges to the zero, almost zero error, and it goes on. So this convergence time can be improved using unscented Kalman filters, and then we go for the long time performance. So here you can see that this extended Kalman filter is going up and down. It's still within the range of plus minus 2 degrees, but we can see that unscented type filters have better performances. These jitters are not, sudden jitters are not there in unscented type filters. And this is for roll. This same thing is happening. So you can see this, there is bit high, EKF is going bit high error. So that's pitch, and in yaw is actually at some point the EKF is having 5 degree of error, and then it's coming back and -5 degree and then stabilization.
So at that point there, that's when the CubeSat went into eclipse. And shortly after, the UKF also went into eclipse. But you can see the EKF responds not as well as the UKF to losing that extra measurement.
So that is a gyro bias error estimation. So here the bias estimation error is all the filters have similar estimation error, and then finally we let's see what is the computation time improvement. So we are comparing all the filters with respect to the extended Kalman filter. So computation cost for extended Kalman filter is 100%. So we are comparing with itself, and for UKF it's 20 times higher. 20 times higher, and if you see the RMSE error in each axis, EKF has almost at least 1 degree RMSE error in each axis, and in UKF it is giving very lower error, but computation time is 20 times high. You can see that the error by SPUKF and ESPUKF are almost at the order of the UKF, but the processing time is only 142% compared to the EKF, and ESPUKF is 256. So 2.5 times increase in SPUKF and around 1.5 times increase in ESPUKF. So conclusion and future work. So these preliminary results show that unscented type filters provide better estimation performance for attitude determination problem. So, and then the processing time of SPUKF and ESPUKF are significantly reduced, and then unscented type filters show better stability during the sun visibility, the eclipse transition time. And the new filter, our future work is that implementing the new filters in UNSW eco engineering model and get a more realistic results. So that's it. Thank you very much.